is the data categorical or so we want to first, how do I fix? Please a minute. Okay, thank you. So we now have our research question and we have our data. So looking at your data that you have, you ask yourself, is the data categorical or continuous? So if it's categorical, then we go with what? The non-parametric test for what we've discussed so far. And if it's continuous, then you ask yourself some questions. Is the data normally distributed? Is it satisfying the assumption of the parametric or not? If yes, then you go with what? The parametric test. And if no, you go with what? The non-parametric. So let's say our data is satisfying the assumption. So it's normally distributed. So I'm going with the parametric. Then you ask yourself another question. Is my research question talking about comparing groups or it's talking about relationship? So if I'm talking about differences, comparing, then I'll ask myself, am I comparing 2 groups or 3 groups? So if it's 2 groups, then I'm going with what? The t-test. So now you are at the t-test, then you also ask yourself, am I comparing 2 independent groups or am I dealing with what? A pair t-test? And so that will help you decide which kind of data you have to go with. Which test you have to go with. But if it's 3 groups, then we go with what? The ANOVA. And under ANOVA, we've learned the one-way ANOVA, two-way, and the repeated. So based on the research question, you decide which ANOVA you go with. But if the question is more about relationship, and that's what the data is also talking about, then you either go with what? The correlation. And if it's more of like asking extra, can X predict Y, then you go with what? The regression. You go further steps from the correlation to the regression. But let's say the data is not parametric, then we move forward to what? The non-parametric. So with the non-parametric, you also ask yourself, is it categorical or continuous? If it's categorical, we have these types that we are supposed to go in for. And if it's continuous, you ask yourself, is it differences or relationship? So if it's differences, like we did for the t-test, the ANOVA, this is the same as it. But with this, we go in for what? The Mann-Whitney test, the Kruskal-Wallis, the Wilcoxon, and the rest. And if it's about relationship, we go in for what? The Spearman correlation and Kenda. So this like short scenario that from the decision tree. So I hope this one we can easily remember. When you're comparing 2 groups, you ask yourself, if it's parametric, then, and if it's independent, we use what? The independent sample t-test, or if it's non-parametric, we use this. And if it's 3 groups, ANOVA comes in for parametric. And if it's non-parametric, we are using a Kruskal-Wallis. And if I'm talking about relationship, then I'm using what? Correlation, Spearman correlation, Pearson correlation, sorry. And for the parametric, and if I'm using the non-parametric, we are using the Spearman correlation. Likewise, we do for the count. But always, the number one thing is to confirm assumptions before deciding on the test to use, or else you end up wasting time and being confused. So some common mistake we want to avoid. And based on what we've learned so far, we know we can avoid this kind of mistakes, like using the wrong test for the question and using like ANOVA t-test instead of ANOVA. We can also ignore like Another mistake that you want to avoid is what? Ignoring the data type and the structure. So if you know our data type, we can go in for the right test to use. And one more important thing that we shouldn't ignore was the assumption. If you follow the assumption right, it makes it easier for us. And when we have done the test, we now have to interpret it. So when we are interpreting our test, we are looking at what the p-value and other important things. So most of the times, our test, we go in for, let's say, alpha level of 5%. So we want to interpret our p-value. And the p-value mostly tells us whether an observed effect could be due to chance or not, but it does not tell us whether that effect is big or small. And most of the times, we want our p-value to be very small to make it statistically significant. But if it's statistically significant, doesn't necessarily mean that it is practically important. For example, if I do a test on a drug to see if that drug can reduce blood pressure. So for example, I do the test and before the test is the blood pressure is 120, after it is 118. So the effect there is 2, the difference is 2. But my p-value is very, very small, like let's say p-value is for 0.002. It's less than 0.05. So it's statistically significant, but the effect there is not really, really meaningful because the difference is that 2. But let's say before the test, it was 120, and after the test, it was 100, and the p-value is 0.04. This is statistically significant though. Even though it's higher than this, it's significant. But the effect here is better because we can see that it has a bigger effect compared to the first one. So we should equate statistical significance with what? Practical importance. And another thing we're supposed to also look at is that when we are interpreting it, we should stay within the limits of the data. So if I take this, let's say a class of 44, and I did a test on it, and I'm using that 44 people to make conclusion on all human beings, I'm going beyond the data. And that's like kind of extrapolating, and this gives us a wrong interpretation. And sometimes there will be a correlation. So we always say that there's like a relationship between overspeeding and accident, but it doesn't necessarily mean that the speeding caused the accident. So we shouldn't always confuse the correlation with the cause of it. And I've said the effect size. So when you're interpreting the p-value, it's better to add the effect size to it to make a complete explanation. So we'll now go on to the demonstration to see them. Sorry, we'll now go on to the demonstration. Just lost the chat. Sorry. All right. Stop sharing for just a second and pull up the code. Okay, is this in a large enough font for everybody to see online and in person, or should I zoom in on the code? Can you see it okay?
You can make the font bigger.
Okay, I'll try to make it a little bigger, like maybe that's a little better.
The color, I don't know, the green looks a little bit. But I can see from my laptop, I don't know the guys online.
She can do anything about it.
Can change the color.
Yeah, that's thing like.
Okay. Okay, so let's go ahead and get started on a demonstration here.
Sachi's going to be watching the chat now, so if you have any questions, you can put them in the chat, and in person, you know, just you can raise your hand and stop me if you have questions too. So the goal here with this code is we want to demonstrate the commonly used statistical tests for a variety of data sets. So your data really depends on the test you're going to use, or the test depends on your data. So let's just go ahead and get into it. So we're just going to start with a couple setup codes. So all this line of code does here is if you had been working in R previously and you had a bunch of variables stored over here in your environment, when you run this line of code, it's going to clear everything so you have a fresh start. Okay, and then all of these packages here are what we're going to use throughout this code. So each of the packages has their own kind of purpose. So that's what all these little comments I have here are. So we'll go ahead and run all of these, and you only have to run it once. Okay, I don't need it. No, I don't need to restart R.
You just have to press no.
Okay, I don't know why it's telling me that, but I'm pretty sure I've already installed all these packages, so I'm just going to go ahead and run the library. You only have to run the install packages if you have never installed them before. So I'm pretty sure, maybe it was just giving me that because I had already had them installed. But once you install all these, you can go and call the library so that you could actually be working with this library. And by the way, if you're unfamiliar with R, I should have mentioned this at the beginning, but there's two ways that you can like run a line. So there's a keyboard shortcut. You can run it by pressing Control Enter on Windows or Command Enter on Mac, I believe. And then you can also run by clicking this button up here at the top that says Run. Okay, so continuing on, this is just a little helper function that I made. So ChatGPT wrote this for me, so don't like expect to know the syntax. It's hard to remember syntax unless you work with it every single day. Like I remember install packages, but I'm not going to remember how to write this function every single time unless I do it every single time. So all this does for me is run a Shapiro test, which checks for normality whenever I have a bunch of groups. Okay, so it's easier than running the Shapiro test one by one. And so that's why I just made this short little function. So I'll show you how it's used later. But for now, we can just go ahead and run it. And now it pops up over here in our functions defined. Okay, so let's go ahead and start by looking at an example where we would use a one sample t-test. So all the data that we're going to use in this workshop is already built into R, and so it'll just be like called throughout the code, so you don't have to worry about uploading anything. Can you not see it because it's too small, or you can't see like my screen?
I'm seeing you and not the screen.
Did you share the screen?
Yes.
Anyone else having that issue?
No.
Interesting. Okay, sorry, go on.
Okay, sorry. All right. Okay, so going on with the one sample t-test. Let me just do a quick check. Was everyone able to get to this point where they've loaded the data or loaded the script if you were going to follow along? Otherwise, I could help you get to this point. Okay, in person, you guys were able to pull it up? Okay. All right, Sorry, I meant to check for that at the beginning. But okay, let's go ahead and continue with our one sample t-test. So the data we're going to be using for this one is the MT cars. It's a built-in data set, like I said. And it has the characteristics of the cars for 32 different cars. So our outcome variable is the miles per gallon. It's a continuous variable. And then this works well for the one sample t-test because we want to compare the sample mean of the one continuous variable to a known value. So I put a research question up here. This could be a possible research question if you're working with this data set. So we want to know, is the average miles per gallon in this sample different from 20 miles per gallon? So let's just go ahead and look at the top of our data so we can understand. So yeah, so this row here is our miles per gallon. So that is our outcome, and that's what's important to us. So then we'll go ahead and run the summary. And so let's just look at this here. We can see the mean, and we see the mean of the data is already at 20.09. So the research question is the average MPG in the sample different from 20 miles per gallon? So looking at this mean of the data is at 20.09. So we can kind of just use context clues and say, it's probably not going to be different from 20 miles per gallon. But what this test does, it gives you a definitive answer in statistics, is if it's going to be different from this value. So let's just go ahead and check our distribution. Again, we want our data to be like roughly normally distributed, and it's going to look like a bell-shaped curve. So if our data, this is like the golden standard. We want it to look like this bell-shaped curve, like, well, that's not the best bell-shaped curve, but it's one. Oh, it's okay. I've got the camera where they can see, I think. But then this data kind of looks roughly normal, but it's more like, and then maybe a little bit up on the end, just due to the last couple of cars having the miles per gallon be between 30 and 35. So we can't say for sure if it's normally distributed or not. So let's look at a QQ plot. And this is also another way to test if you have normality in your data. So let's go ahead and run that. And if I pop that up, can they see that? No, it's not popping up. It's on the corner, but that's fine. So if you see this plot in the bottom right corner, if this data were perfectly normally distributed, you would see all of the points follow along this straight line. But looking at this plot now, it's not that bad. So I mean, you see a little bit, a few points like above the line over here, and that could just indicate like a heavier tail. So what I mean by heavier tail is maybe you have more data on this end of your data. So you have more like on this side whenever it should be towards the center, but you have a heavier tail possibly from, and that's how I would interpret this plot. So here's the Shapiro test, and we're just going to go ahead and run this, and it gives us a way to formally check normality without kind of just interpreting the plots. So let's go ahead and run that. And if we look at our p-value, we've got a p-value of 0.1229. So that tells us that the normality assumption is met because it's above 0.05. Okay, so that means that we can reject the, is it reject? Okay, so we do not reject the null, and normality is met. So then we know that we have to have normality to run a t-test. So let's go ahead and run our one sample t-test. Okay, let me pull up that a little bit. Okay, so for our t-test, we got a p-value of 0.9328. So that means we do not reject the null. So that means true mean is not equal to 20. Or wait, no. Is not statistically significantly different from 20 is what I mean. Sorry. Should have just read my notes. So the confidence interval, let me just highlight that here, also includes 20. So there's no evidence of a difference. All right, let's go ahead and move on to our next. Okay, we're going to do the independent two-sample t-test now. So now we're going to move on to the tooth growth data set. And this data was collected on a bunch of guinea pigs. They measured the length of the guinea pig's teeth, which I don't want to think about the logistics behind that. But it's a pretty cool data set. Anyways, our continuous outcome is the length. That's what we care about. That's what we're going to be looking at. Sup is the supplement type. So there's two supplements. There's orange juice and vitamin C, labeled as OG and VC. And then dose is the dosage level, but we're only going to be working with the one dosage level so that we can compare the two groups, the OJ versus the VC vitamin C. So with that, our research question is tooth length different between supplement groups? Okay, well, let's find out. So first to start, these two lines of code are going to make R see these variables as categorical. Because by default, whenever you load data into R, it's just continuous. So whenever you tell it it's as a factor, now it sees it as as a categorical variable with two groups. So one being OJ and one being vitamin C. And then it was the same thing for dose. In the original data, there's, I think, 3 different doses, but again, we're only going to use this one, and we filter that out down here. So I'll go ahead and run these. Okay, and really quick, we can look at the data. So let me do that. So just two things, or a couple things you can see whenever you look at the summary of the data down here is both groups have 10. So there were 10 guinea pigs that were given orange juice, 10 guinea pigs that were given vitamin C. Now those guinea pigs that were given orange juice had a mean tooth length of 22.7. I'm not sure what the units are, but that seems pretty large for teeth. We'll see. I'll have to see what the units are. That's interesting. Okay, so the guinea pigs that were given the vitamin C had the mean tooth length of 16.8. Okay, so based on that, it seems like there's a difference. It seems like the supplement matters. So that's just what we can infer kind of intuitively. So let's go ahead and look at a box plot. If you look at the orange juice one, it seems most of the values are much higher than, yes.
I don't know if it's my version, but I don't have the piping function. Is it in the DPR or in the tidyverse?
Hang on 1 second. Let me look. It's okay.
I can't proceed with the box further. I tried loading this and this is the error I got, like I don't have.
Could not find function. Oh, you have to run the libraries. So
Okay, I just did this.
it might be a different library. Try and go back to the top and run all of your libraries again. And make sure all of them were able to install properly. And let me know if you still have an issue. Okay. So back to our box plot. It seems like the tooth lengths for guinea pigs that were given orange juice are usually higher than the ones who were given vitamin C, except with this one special outlier guinea pig for vitamin C. He had a longer tooth length than the rest of them. So let's go ahead and check our normality assumption. So this is the QQ plot for the orange juice group. And, there's two little points that kind of fall off the line, but it seems like generally normal. Let's look at vitamin C. This point that's like way off over here is probably most definitely the outlier that we saw in the box plot. So this is kind of expected, but it doesn't necessarily mean that normality assumption was violated. So let's do, and here's that function I defined at the beginning that's going to let me test multiple groups at once. So let's go ahead and run that and do the formal test for normality. So our p-value is at 0.41 and 0.26. So that means that both groups do have normality. Okay, and then this Levine test, it just does a test to check for equal variances across groups. You usually do this just to check for homogeneity whenever you have more than one group. So let's run that. And our p-value is at 0.2123. So again, that's good. And we do have equal variances. Okay, so finally, let's run our t-test. Okay, so here's our p-value. So that's very low. So what this test is going to tell us is whether the mean tooth length differs between the two independent supplement groups. So does it differ between orange juice and vitamin C? Well, from the box plot, we would guess yes. But now we have a t-test that tells us that it is statistically significant. So instead of guessing yes, it's definitely yes. There is a significant difference in mean tooth length between supplement groups because the p-value is very low. And like we saw earlier as well, guinea pigs receiving the orange juice have higher tooth length than those receiving vitamin C. All right, let's go to our paired t-test now. So now we're going to use the sleep data. Just go ahead and print the head of the data so we can talk about it. So it's another built-in data set. It compares the increase of sleep from two drugs across the same 10 subjects. So this is a repeated measures data set. So because of that, we want to put the data into a wide format to make it easier for the paired test. So let's go ahead and run that. That's all this code does is change the format of the data. It doesn't change anything about the data itself, but I'll just go back and show you. So like the original data, it has the group as a column, the ID as a column, and then the extra as a column. So now each row, this is the entire data set, and each row is the person, and it was the person when they're in group 1, group 2. So now it's going to be easier to do our test. Okay, so what the paired t-test is doing is testing whether the mean difference is 0. So we want to check the distribution of the difference scores rather than each original group separately. So instead of testing group 1 and group 2, we're going to take the difference. So what we're going to do is we're going to subtract group 1 from group 2. And all this code does is make it into its own column so that we could do like plotting and analysis with it. So I'm going to run this first line, and then we're going to get the histogram of that. And again, we would like it to be normal. It's a small sample size. There's only 10. So you could say maybe it's normal, but let's look at the other methods of checking that. So it looks like there's an outlier, but most points fall along the line. So it could possibly still be normal. So then let's do the formal check. And then we get to our formal check and our p-value is low. It's 0.03. So that tells us that normality is not necessarily met. But we can say it's close. So I know this is a parametric test, and like we kind of just beat it into you that you have to have normality to run a parametric test. That's the whole point. And that's still true, but you can still run the test and look at your outcome. So what we do for this specific instance is we're still going to run the test, we're still going to interpret it, but then later down the road, we're going to use the same data and look at the non-parametric alternative. And then even though we didn't have normality, we can look at the non-parametric alternative and kind of group the results together. So whenever you don't have exact normality for a parametric test, it's not necessarily you can't interpret it whatsoever. It's just use caution. It doesn't always lead to the most true results. So you just check as many things as you can. So let's run this paired t-test. So we've got this very low p-value of 0.002, 0.0028. And so that tells us there is a significant difference between the two drug conditions. And then the mean difference down here is negative 1.58. So that means that the two groups, or that group 2 leads to more sleep increase than group 1. Okay, and then right now we're going to move on to the one-way ANOVA, but later I'll show you the non-parametric alternative to this, and we can kind of double check the results. Okay, so next we're going to work with plant growth data. I'll go ahead and print the top of that. So we've got our continuous outcome of weight, and then we've got 3 different groups. We've got control, which in the very top of the data, you can't see the other 2, but there's control, and then treatment 1 and treatment 2. So again, this here is just going to let us identify this group variable as a factor. Therefore, R is going to see it as categorical now instead of continuous. And then our research question for this, it's ANOVA. So now we are going to be working with 3 or more groups. So are mean plant weights different across 3 treatment groups? So this is just going to give us a little summary of the data. Yeah, so here's our 3 groups: control, treatment 1, and treatment 2. Each of the groups have 10 participants, or 10 plants, I guess. And here's the mean weights. So they look pretty similar, but we're going to let ANOVA tell us if they're different. So let's just look at a box plot. So it really looks like treatment 1 and treatment 2 are the most different. treatment 1 has an outlier. So we'll just keep going and let ANOVA tell us if they actually are different or if they're all the same. But first we got to check normality. So here we go. Here is the QQ plot for control. It looks decently normal. It looks like it falls mostly along the line. Kind of the same thing for treatment. Maybe these two are outliers. That's definitely possible. I think treatment 1 did have an outlier when we looked at the box plot. Let's look at treatment 2. And something similar for treatment 2. We do have a little bit, maybe a heavier tail in this end, but again, the sample size is small. So we shall see. And then I'm going to use that helper function that we made at the beginning again to do the formal normality test for all of the groups. And let's just do a quick look. P-value is high, p-value is high, and p-value is high. So that means that all groups, the normality assumption is met. So good. And then we'll go ahead and do the Levine's test again to check if we have the equal variances. Okay, our p-value is high. We have equal variances. That's great. Let's go ahead and do ANOVA. So we've got our weight, which was our continuous outcome that we wanted, and then the group. Let's run our model and get the summary. Okay, so we got our p-value of 0.01. So this tells us that at least one group mean differs from the others. So the ANOVA doesn't tell us which one. It doesn't tell you if it's control and treatment 1, or if it's treatment 1 and treatment 2, or control and treatment 2. It doesn't tell you which. It just tells you that, yeah, there is one. Okay? So that's why we do this test here. This is called the Tukey's on a significant difference. And if you run that on our ANOVA model, it's going to give you a p-value for each one. So this is the low p-value. These other two p-values are high. Okay, well, the first one was for treatment 1 and control. The second one was for treatment 2 and control. So there's no significant difference between those groups. But whenever we look at treatment 2 and treatment 1, there is a statistically significant difference. So the relationship between these two is what's causing, or the differences between these two is what's causing the ANOVA model to be significant in general. And now we have this test that tells us which two groups cause that. Okay. So let's go ahead and move on to the next one. We work with the Titanic data. It's a very popular data set in R, so I'll just go ahead and print the top of it so we can see. So each person had a class. There were 4 different classes, male or female, the age, whether they survived or didn't, and then the frequency. So the research question for this one, since we're going to do a chi-squared test of association, we want to know, is survival associated with passenger class? So in order to do that, we're going to put the data into a table. And I'll just show you that. So we did it by class against whether they survived or not. So for first class, 122 people that were in first class did not survive. 203 people who were in first class did survive. And the same with second, third, and crew. So then let's go ahead and run our chi-squared test. And if we look at this, we have a very low p-value. So that means that there is a strong association between passenger class and survival. So that means that your class did matter. And that tells you, if you look at someone's class, you could probably guess whether they survived or they did not. But one thing to note about when doing chi-square tests is you have to have a sufficiently large sample size. So that's what this this line of code does here. It just checks that. And all the numbers are large, so that tells us that we're good to go. Okay, so let's just, to finish out this test, we're just going to look at a plot. I did add this part after I sent out the script to you guys. So the only reason I did that is because it was having a problem. The legend was actually covering part of the graph. So if you don't have that issue, you don't have to worry about changing anything. You can just run what I left in the script. But I'll go ahead and run these. What covered it again? Let me see if I make it bigger, if that makes a difference. Okay. Yeah, I thought I fixed that issue, but these two bars that are kind of hidden, they're similar to this blue bar here. So think of it as kind of like all the same size. So, but if you look at this graph, that kind of tells you that you really didn't want to be a crew member or a third class member, because they did not survive as often as the first and second class members. Okay. So let's go ahead and do this next test. It's the Fisher's exact test. It's kind of give you the same result as the chi-squared, except now you can have small sample sizes. And I know that we're running out of time, so I'm going to try and like move fast through the rest of this. Feel free to go if you have time constraints. And if I run through fast, feel free to shoot us an email. But okay, so we just define a quick small matrix here. And that's going to be our data. And then I just make some column names, some row names, and let's look at that table that we made real quick. So we have a treatment and we have a control. In the treatment, we had 1 success and 9 failures. And the control, we had 8 success and 2 failures. Okay, so let's go ahead and run this test on this small table that we made. So we've got a p-value that's very low. So that tells us that there is a significant association between treatment and outcome. The odds ratio also down here is very small, and that would suggest that treatment greatly reduces failure or increases success. Okay. Scroll down. Okay, we're going to go back to using the first MT-CARS data set. And we're going to look at the Pearson correlation. So we're going to ask the question, is car weight related to miles per gallon? So here's just a plot of the data against each other. So it looks like as weight of the car is increasing, the miles per gallon is decreasing. And that makes sense, because the heavier your car is, the less gas mileage you're going to get. So let's go ahead and run our correlation test. Pull it up a little. So we have a very low p-value. So that tells us that there is a strong linear relationship, but we know it's negative because we got this value of 0.87 when you round. So that tells us that there is a strong negative linear relationship. So kind of what we guess from the graph is that as car weight increases, miles per gallon decreases. And this tells us, in fact, that that is true. So next, we'll just do a simple linear regression. We just want to know, can miles per gallon be predicted from car weight? And from above, they were highly correlated. So I'm gonna say I can infer that probably the answer is yes. So I will run the model. And we get our output, and our p-value is very low for both, or for the weight. So that at least means that there is a statistically significant relationship between miles per gallon and weight, which we knew from the correlation. So let's plot. Okay, so now we have our regression line on the data. So usually whenever you do linear regression, you have to check assumptions. There are 4 assumptions that you have to check. It might not let me run this. Oh. Okay. Let me see if I can share it where you guys can online can see it, because I know you can't see it. Okay, now you can see it. See that. So this is how we check if there are outliers, if there are leverage points, if the data follows a normal distribution, if there's non-constant variance, all of the above. So all of these plots help you determine if your assumptions are met. So the same thing with the QQ plot of the residuals. We saw QQ plots earlier. It looks like maybe the data is mostly kind of normal, but there's also some outliers up top. And if you look at the residuals versus leverage plot, it kind of looks like you could see those same outliers. The text is overlapping, but it looks to me like they're the same cars that are appearing. And then if you look at your residuals versus fitted, you want this to have approximately no slope. You want this to be randomly scattered. It looks like maybe there might be like a nonlinear pattern, like maybe quadratic or something. Let's see. Okay, let me go back to sharing my code. Okay, so our simple linear regression is going to estimate how miles per gallon changes as car weight changes and whether weight is a significant predictor of miles per gallon, which we determine it is because the p-value is significant. So if we want to go back and interpret the coefficient that we got from the summary, let me just show that real quick. The coefficient, this is our coefficient for weight. So if we want to go back and interpret that, so that means for every 1 unit increase in weight, miles per gallon decreases by about 5.34 units. And then where's our R squared? Here's our R squared value. So this is a decent model because R squared, if you're not familiar, is the coefficient of determination. And that value tells us how much variation is being explained by the model. And then whatever's left is just random, usually. So R squared of about 75% is decent because that means the model is explaining, or weight is explaining 75% of variation in miles per gallon. Okay, so here's our non-parametric alternative to the independent t-test. We're going to reuse our tooth growth data. Is that the one that was non-normal? There was one that I said, I'll show it was the, oh, so is that sleep?
Yeah.
Okay, well, here's our non-parametric alternative to the independent t-test. So remember, we're reusing our tooth growth data that we had on the guinea pigs, and we've got a low p-value. So this test is going to evaluate whether two independent groups differ in their distributions without assuming normality. So it's the same result we got earlier, except now we don't have to worry about having normality. So looking at our low p-value again, there is a significant difference between the two supplement groups. This confirms the t-test result without assuming normality. So like I said, it was the same result as earlier, except now without normality. Okay. Where am I at? All right, I'm getting to the end now. I think there's only like 2 left after this. So I'll try and hurry up a little bit. So now we're going to do our Wilcoxon sign rank test. And it is our non-parametric alternative to the paired t-test. So I'm pretty sure this was the one where the data was not normal, the sleep data. So I said we're also going to check, we went ahead and did the parametric test on the sleep data earlier, but we're going to look at the non-parametric alternative and see if both have the same result. So let's look at that now. So we'll go ahead and run our test. And we have a very low p-value. So there is a significant difference between the paired conditions. And this confirms that the paired t-test result are the same thing that the paired t-test result gave us earlier without assuming normality. Okay, then let's look at it finally. Or wait, I think there's one more after. Okay, so we have 2 more to cover really quickly. So here's our non-parametric alternative to the one-way ANOVA. This data that I'm going to use on this one is the insect sprays. So let's just go ahead and look at the top of it. I think there are 5 different sprays. Yeah. So we'll go ahead and make sure R sees that as a categorical variable. We'll do a box plot. You guys probably can't see that. Let me share that again. 1 second. Okay, so here is our box plot of the insect count by spray type. So it looks like spray type C, D, and E are very different from A, B, and F. C and D does have some outliers, but on average, it looks like their amounts or their count are much smaller. So let's go back to our test. So we're going to do the test that's going to tell us whether at least one of the group distributions differ from the others without assuming a normal outcome. So let's run it. Again, very low p-value. So there is a significant difference across spray types. At least one spray has a different effect, but you'd need a post hoc test to see which. So the same thing that we did for the ANOVA above, we did the Tukey HSD. You could do something similar for the non-parametric to see which spray type is causing the difference overall. Okay, final test. We've got our Spearman correlation. It's our non-parametric alternative to the Pearson correlation. So we're going to reuse our MT-CARS data set again. Let me make this a little bigger. And run our test. So if you got that warning message, don't worry about that. It's just telling us it cannot compute the exact p-value. That's not a big problem as far as I know. So Spearman correlation measures the strength and direction of a monotonic relationship based on ranks rather than the raw values. So if we look at our p-value outcome from our Spearman rank test, there is a strong negative monotonic relationship, and we can tell that by looking at our p-value and our rho value, which is a negative and large. So we can conclude that as weight increases, miles per gallon decreases, even when considering rank-based relationships. All right, and then I have just a little summary to wrap it up here. So here's just kind of a small guide to help you pick the test for your own data. So look at your own data and ask these questions. Is it going to be a difference, relationship, or association? Is your outcome continuous or categorical? What's your number of groups? Is it independent or paired? Are your assumptions met? And so based on your answers to these questions, it should help you pick the right test for your specific data and research question. And then here's just a couple like common matches. One sample t-test, 2 groups, independent t-test. And if it's non-parametric, here's your alternative. And you can just look at these common matches and compare it to your own research. And then finally, in some situations, like maybe you want to use a parametric test just to be more, what's the word I'm looking for? It's stronger. It's stronger than using a non-parametric test. So maybe let's say you have non-parametric data, but you really want to use a parametric test. Well, data can be transformed or normalized so that a parametric test may become more appropriate. Doing that is outside of the scope of this workshop. I think that's like a whole half a semester of a class, but it is doable. So you don't have to be stuck with non-normal data. So if that's something you would be interested in, I would recommend looking into transformations or normalization. And that's going to conclude our workshop. I'm going to stop recording